Introduction to Quantum Mechanics. According to Wikipedia, quantum mechanics is the study of matter and its interactions with energy on the scale of atomic and subatomic particles. By contrast, classical physics explains matter and energy only on a scale familiar to human experience, including the behavior of astronomical bodies such as the Moon. Classical physics is still used in much of modern science and technology. However, towards the end of the 19th century, scientists discovered phenomena in both the large, macro, and the small, micro, worlds that classical physics could not explain. The desire to resolve inconsistencies between observed phenomena and classical theory led to two major revolutions in physics that created a shift in the original scientific paradigm: the theory of relativity and the development of quantum mechanics. This article describes how physicists discovered the limitations of classical physics and developed the main concepts of the quantum theory that replaced it in the early decades of the 20th century. It describes these concepts in roughly the order in which they were first discovered. For a more complete history of the subject, see History of Quantum Mechanics. Light behaves in some aspects like particles and in other elements like waves. Matter, the stuff of the universe consisting of particles such as electrons and atoms, exhibits wave-like behavior too. Some light sources, such as neon lights, give off only certain specific frequencies of light, a small set of distinct pure colors determined by neon's atomic structure. Quantum mechanics shows that light, along with all other forms of electromagnetic radiation, comes in discrete units, called photons, and predicts its spectral energies, corresponding to pure colors, and the intensities of its light beams. A single photon is a quantum, or smallest observable particle, of the electromagnetic field. A partial photon is never experimentally observed. More broadly, quantum mechanics shows that many properties of objects, such as position, speed, and angular momentum, that appeared continuous in the zoomed-out view of classical mechanics, turn out to be, in the very tiny, zoomed-in scale of quantum mechanics, quantized. Such properties of elementary particles are required to take on one of a set of small, discrete allowable values, and since the gap between these values is also small, the discontinuities are only apparent at very tiny, atomic, scales. Many aspects of quantum mechanics are counterintuitive and can seem paradoxical because they describe behavior quite different from that seen at larger scales. In the words of quantum physicist Richard Feynman, quantum mechanics deals with nature as she is, absurd. One principal paradox is the apparent inconsistency between Newton's laws and quantum mechanics, which can be explained using Ehrenfest's theorem, which shows that the average values obtained from quantum mechanics, e.g., position and momentum, obey classical laws. However, Ehrenfest's theorem is far from capable of explaining all the counterintuitive phenomena, quantum weirdness, that have been observed, but rather is a mathematical expression of the correspondence principle. For example, the uncertainty principle of quantum mechanics means that the more closely one pins down one measurement, such as the position of a particle, the less accurate another complementary measurement pertaining to the same particle, such as its speed, must become. Another example is entanglement, in which a measurement of any two-valued state of a particle, such as light polarized up or down, made on either of two entangled particles that are very far apart causes a subsequent measurement on the other particle to always be the other of the two values, such as polarized in the opposite direction. A final example is a superfluidity, in which a container of liquid helium, cooled down to near absolute zero in temperature, spontaneously flows, slowly, up and over the opening of its container, against the force of gravity. The first quantum theory, Max Planck and blackbody radiation. Thermal radiation is electromagnetic radiation emitted from the surface of an object due to the object's internal energy. If an object is heated sufficiently, it emits light at the red end of the spectrum, as it becomes red hot. Heating it further causes the color to change from red to yellow, white, and blue, as it emits light at increasingly shorter wavelengths, higher frequencies. A perfect emitter is also a perfect absorber. When it is cold, such an object looks perfectly black, because it absorbs all the light that falls on it and emits none. Consequently, an ideal thermal emitter is known as a black body, and the radiation it emits is called blackbody radiation. Predictions of the amount of thermal radiation of different frequencies emitted by a body. Correct values predicted by Planck's law, green, contrasted against the classical values of Rayleigh-Jean's law, red, and Wien approximation, blue. By the late 19th century, thermal radiation had been relatively well characterized experimentally. However, classical physics led to the Rayleigh-Jean's law, which, as shown in the figure, agrees with experimental results well at low frequencies, but strongly disagrees at high frequencies. Physicists searched for a single theory that explained all the experimental results. The first model that was able to explain the full spectrum of thermal radiation was put forward by Max Planck in 1900. He proposed a mathematical model in which the thermal radiation was in equilibrium with a set of harmonic oscillators. To reproduce the experimental results, he had to assume that each oscillator emitted an integer number of units of energy at its single characteristic frequency, rather than being able to emit any arbitrary amount of energy. In other words, the energy emitted by an oscillator was quantized. The quantum of energy for each oscillator, according to Planck, was proportional to the frequency of the oscillator. The constant of proportionality is now known as the Planck constant. The Planck constant, usually written as h, has the value of 6.63 times 10⁻34 J/s. To change the color of such a radiating body, it is necessary to change its temperature. Planck's law explains why. Increasing the temperature of a body allows it to emit more energy overall, and means that a larger proportion of the energy is towards the violet end of the spectrum. Planck's law was the first quantum theory in physics, and Planck won the Nobel Prize in 1918 in recognition of the services he rendered to the advancement of physics by his discovery of energy quanta. At the time, however, Planck's view was that quantization was purely a heuristic mathematical construct, rather than, as is now believed, a fundamental change in our understanding of the world.